Structures subjected to induced vibration, such as road load or fluid flow, experience dynamic energy that can't be quantified simply by frequency and amplitude. Because fatigue properties are usually frequency dependent, a mix of frequencies cannot be handled in the traditional manner. Autodesk Nastran in CAD's random vibration fatigue analysis is the solution to this problem. A vibration fatigue analysis is actually 3 analyses. It starts with the frequency response analysis, or a harmonic excitation where the model is loaded harmonically across a range of frequencies. This is followed by a random analysis with the results of the frequency response analysis scaled and combined according to a power spectral density function that describes the variation of vibration with frequency. A PSD may come from a vibration testing and measurement. Finally, it's time to run the fatigue analysis itself. The fatigue analysis takes the results of the random analysis, specifically stress levels and the pseudo-frequencies, and will generate the traditional fatigue life and number of cycles until failure. The actual lifetime is computed from the pseudo-frequencies generated in the random analysis. Vibration fatigue is slightly more complicated to set up than many other types of analyses. We will demonstrate the setup of a random fatigue analysis with this support bar model. First off, the sample model will be held in 2 places. There will be a sliding bearing-like constraint here, and it will be fixed to the wall here. We will apply a harmonic load to the ball joint. For the purposes of random response, this will be a unit load that will be scaled by the PSD. From a structural point of view, we were concerned with the small machined grooves on the model. When the model was meshed, Autodesk Nastran in CAD automatically generated a fine mesh in those areas to resolve the expected stresses properly. After defining the PSD, we are ready to run the model. The final objective of this analysis is the fatigue life plot, similar to what you would get from a traditional fatigue analysis. This plot shows the lifetime of the part in number of cycles. You can see the fatigue life varies from 0, here in the blue areas, which are overstressed on even a single cycle, to the red areas that are not stressed significantly and have an infinite fatigue life. Because the other steps that went into this analysis, we get more out of this process than just the fatigue life. We get a whole series of results, such as the response of the structure to excitation from the frequency response analysis, as well as a power spectral density function from our random analysis, but the more important results are down at the bottom. These are the RMS results that represent stress and deformations in a statistical manner as a result of the random excitations. Finally, you have the NPX, or net positive crossings, which are the pseudo-frequencies that represent the equivalent frequency the fatigue life was based on. So while the goal of this analysis was simply the fatigue life, a whole set of other useful information about the structure is produced along the way. Random vibration fatigue in Autodesk Nastran in CAD provides engineers with long-term insights to a product's robustness and dynamic behavior.